Limits for sequences obey the same kind of rules and laws that we had for limits of functions. So this for convergent sequences, so as long as the sequences already have limits, then this limit of a sum of sequences will be the sum of their limits, and the limit of their differences will be the difference of their limits. And if I know the limit of a particular sequence, then I can find the limit of any constant times that sequence. It's also true that the limit of a constant sequence, so this is a sequence where every term is c, that will be that constant. If the limits of the sequences exist, I can find the limit of the product as the product of the limits. The quotient one works as long as the limit of the denominator doesn't go to 0. And this power one is really useful. So if I raise a sequence to a power p, where p is a positive power, not a function, a fixed power, okay? Like say we were looking at n over n plus 1 to the fifth, and I wanted to know the limit of that sequence. Then the way I can go about this is by finding the limit of n over n plus 1 itself, and then once I find that limit, raise it to the power. So this applies as long as every term of the sequence is positive and the power p is greater than 0. Let's talk about the squeeze theorem. So the squeeze theorem, probably some of you have seen it in Calculus 1. It states that if we have two sequences that happen to have the same limit, and one of them is bigger than the other, and we know of a third sequence that always lands in between. So the image here is I have a sequence, potentially the black dot sequence is going up this way. Sequence a sub n that has one limit, and the sequence cn has the same limit. Then any other sequence where every term lands in between is trapped. It's squeezed, and therefore it has to have the same limit as these other two sequences. So the squeeze theorem can be used to prove convergence if you can bound a particular sequence above and below by two sequences with the same limit. So it's frequently used when you're allowing yourself to do some investigation of what you think the limit of the sequence is already. Here are some other facts about limits and theorems that we can use. If we know the limit of the absolute value of a sequence happens to be 0, this doesn't apply in any other case, then the original sequence had to go to 0 as well. And then this theorem is a nice one. It's a version of what we saw with the raising to a power, but it says if we have a sequence and we know its limit, and then we know a continuous function that's continuous at the value of the limit of that sequence, then it's perfectly fine for us, instead of taking the limit of f of a sub n, to take the limit of a sub n, and then we know its limit is f of that. And often the way we end up using this is by, in investigating what the limit of a sequence is, if the function that we're talking about is continuous and defined for all real numbers, then we can play this game initially. So like, here's an example. Say I want to find the limit as n approaches infinity of e to the 3n plus 1 over 2n. Rather than finding the limit of this exponential all at once, I can do e to the limit. And the reason is because e to the x is a continuous function, and so I can investigate whether the limit of the exponent exists, and I know that exponent exists here. I can see by doing the division in my head what the power is. Or this is e raised to the limit n goes to infinity of 3 plus 1 over n over 2. I divided the top and bottom by n, and because of that, then this limit must be e to the 3 plus 0 over 2, so e to the 3 halves. So that continuous function limit property we use all the time.